Alrighty, hackers and hackerettes, welcome to a new video where we are continuing our network fundamentals in TryHackMe, the pre-security path. The last video we talked about the OSI model, and in this video we are going to talk about packets and frames. Now, if you have not been following along the entire video or like the entire series, I do recommend that you watch the playlist. I do have a playlist called Network Fundamentals, or like TryHackMe Network Fundamentals, something like that. And then in that playlist, watch it in order, because you do want to actually follow along this, because this is gonna be building like on top of each other. So you do want to be having the full context of this. I noticed that the text might be not as clear on recording, so I'm just going to zoom in a bit, so that way it become clearer for you. So we're going to start with task 1. What are packets and frames? Packets and frames are small pieces of data that, when forming together, make a larger piece of information or message. However, there are two different things in the OSI model. Now, if you don't know what the OSI model is, watch the last video. I do have a video here called OSI model, or like OSI model by someone who actually uses it. You're gonna find it in the same playlist. I don't remember the title, honestly. So a packet is a piece of data from layer 3, which is the network layer of the OSI model, containing information such as an IP address and payload. A frame, however, is used at layer 2, data link of the OSI model, which encapsulates the packet and adds additional information such as MAC addresses. So a frame has a packet inside of it. The packet is a data tree or layer 3, but a frame is a layer 2. Okay, so it encapsulates the packet and adds additional information such as MAC address. So the MAC address lives in the frame, but the IP address lives in the packet. Okay, and then a packet lives in a frame as well. You can think of this process as similar to mailing a letter through the post. The envelope is a frame which is used to move the contents, in this analogy the packet, of the envelope to another place. Once the recipient opens the envelope, which is the frame, they will know how to forward the letter, which is the packet itself. Okay. This process is called encapsulation, which we discussed in room 3, the OSI model. At this stage, it is safe to assume that when we are talking about anything IP addresses, we are talking about packets. When the encapsulating information is stripped away, we're talking about the frame itself. Okay? Packets are an efficient way of communicating data across network devices, such as those explained in task 1. Because this data is exchanged in small pieces, there is less chance of bottlenecking occurring across a network than large messages being sent at once. That's why packets are like very small. That's why anything that is large, or not even large, like anything really, gets chunked into smaller pieces and then just sent across, because you could have millions or even billions of packets going in and out at the same like time on the network. So that's why it is essential that each data or each packet is small enough that it gets processed like super quickly, and instead of taking longer to process one packet. For example, when loading an image from a website, the image is not sent to your computer as a whole, but rather small pieces where it is all reconstructed on your computer. Take the image below as an illustration of this process. The cat's picture, okay, so there's no image here, okay, but the cat picture that they are talking about is in the OSI model, which should be in the TCP IP, actually. I do apologize. It's not in the OSI model. It is in the maybe introduction to LAN. No, it is where we were talking about TCP and IP. Not the application, the session, the transport. Yes, TCP. So this is the image, the cat image that they are talking about. So you can see that the cat image, the final cat image right here, is actually split into different packets, and then they are sent across the network as like separate data, separate packets, and then on your computer it's actually reconstructed in order to produce the final cat image. I think they just forgot to include the cat image here. So the image is not sent to your computer as a whole. The cat's picture is divided into 3 packets where it is reconstructed when it reaches the computer to form the final image. Okay. Packets have different structures that are dependent upon the type of packet that is being sent. As we'll come on to discuss, networking is full of standards and protocols that act as a set of rules for how the packet is handled on a device. With billions of devices connected on the internet, things can quickly break down if there is no standardization. Correct. Let's continue with our example of the internet protocol, which is the IP. A packet using this protocol will have a set of headers that contain additional pieces of information to the data that is being sent across a network. Notable headers are time to live, or TTL. This field sets an expiry timer for the packet to not clog up your network if it never manages to reach a host or escape. Checksum. This field provides integrity checking for protocols such as TCP/IP. If any data is changed, this value will be different from what was expected and therefore corrupt. If you don't know how checksum works, I do recommend like you search for a video specifically for it. I'll be making a video probably like in the future speaking about checksumming and how to do some checksums and file information, so on. So you can ensure that what you're downloading is the actual data that you are supposed to get, and nothing has been tampered or corrupted regarding the checksum. The source address is the IP address of the device that the packet is being sent from, so that data knows where to return to. Okay, that's like your mailing address. Destination address is where you're mailing it to. So from and to, essentially, source and destination. Okay. What is the name for a piece of data when it does have IP addressing information? It is a packet. And then the one that does not have an IP address is a frame. Okay, so the frame usually has like a MAC address, and it is the envelope, but the packet itself has the IP address. Cool. Let's get to the second task, which is the TCP/IP. TCP, or Transmission Control Protocol. We have a whole like in the previous video in OSI model, we had a whole task, which is a transport layer, where we talked about TCP and UDP in great detail. One more reason to watch that video if you haven't. So this protocol is very similar to the OSI model that we have previously discussed. So far, the TCP/IP protocol consists of 4 layers and is arguably just a summarized version of the OSI models. Application, transport, internet, and network interface. Very similar to how the OSI model works, information is added to each layer of the TCP model as the piece of data or packet traverses it. As you may recall, this process is known as encapsulation, where the reverse of this process is decapsulation. All right. One defining feature of TCP that is connection-based. It is connection-based, which means that TCP must establish a connection between both a client and a device acting as a server before data is being sent. Because of this, TCP guarantees that any data sent will be received on the other end. This process is named a 3-way handshake, which is something that we'll come on to discuss shortly. A table comparing the advantages and disadvantages of TCP is below. We also talked about this in TCP and UDP stuff, so we're not going to go over it again. TCP packets contain various sections of information, such as headers that are added from encapsulation. Let's explain some of the crucial headers in the table below. Source port. So this is the port opened by the sender to send the TCP packet from. Destination port. Source IP, destination IP, all of these are good. Now the sequence number, when a connection occurs, the first piece of data transmitted is given a random number. We'll explain this more in depth further on, okay? Acknowledgement number, after a piece of data has been given a sequence number, the number for the next piece of data will have the sequence number plus 1. We'll also explain this more in depth further on. Checksum, we already talked about checksum a bit. Data, this is where the data is, and then the flag. This header determines how the packet should be handled by either device during the handshake process. Specific flags will determine specific behaviors, which is what we'll come on to explain below, okay? So we'll continue to discuss, or we'll come on to discuss the three-way handshake, the term given for the process used to establish a connection between two devices. The three-way handshake communicates using a few special messages. The table below highlights the main ones. So one is SYN. A SYN message, or a synchronized message, is the initial packet sent by a client during handshake. This packet is used to initiate a connection and synchronize the two devices together. We'll explain this further later on. Okay, everything is being sent later on. Then SYNAC, the packet, or this packet is sent by the receiving device to acknowledge the synchronization attempt from the client. And then ACK, this acknowledgement packet can be used by either the client or the server to acknowledge that a series of messages has been successfully received. Data, once a connection has been established, data such as bytes of a file is sent via the data message. FIN is used to properly close the connection after it has been completed. That's like finalize. And then REST, this packet, or RST, this packet abruptly ends all communication. Probably not reset then. I think it is reset. This is the last resort and indicates there was some problem during the process. For example, if the service or application is not working correctly, or the system has faults such as low resources. Okay, so this is probably a reset. So the way it works is you send the SYN, like a synchronized attempt, SYNAC, which is like I acknowledge that you want to synchronize with me, and then acknowledge, that means that I got the data that you sent me. The data itself is I'm sending you some data. FIN, like all good, we complete our transaction, nice to meet you. And then the reset is like just no bro, it's not working. This or the diagram below shows a normal three-way handshake process between Alice and Bob. In real life, this would be between two devices. So SYN, Alice sends SYN to Bob. It's like a friend request. Bob texts her, yo, I acknowledge that you sent me a request. I accepted it. And then Alice says, yep, I can see you accepted it. So ACK, or acknowledge. Any sent data is given a random number sequence and is reconstructed using this number sequence and incrementing by 1. Both computers must agree on the same number sequence for data to be sent in the correct order. This order is agreed upon during 3 steps. 1, SYN. The client says, here is my initial sequence number, ISN, to synchronize with 0. All right? SYNAC. Okay, so the very first step is SYN, which is the client. The client says, here's my initial sequence number, ISN, to synchronize with 0. SYNAC, the server says, here's my initial sequence number, ISN, to synchronize with 5000. And I acknowledge your initial number sequence 0. Then ACK, client, I acknowledge your initial sequence number of 5000. Here is some data that is my ISN plus 1, which is 0 plus 1. So that means the client and server do not necessarily have to start with the same number. So you can see the client started with 0, but the server started with 5000. But since now they both know where they're starting from, we could add 1 to it, and that would be the order. You can see right here. TCP closing a connection. Let's quickly explain the process behind TCP closing a connection. First, TCP will close a connection once a device has determined the other device has successfully received all of the data. Because TCP reserves system resources on a device, it is best practice to close TCP connections as soon as possible. To initiate the closure of a TCP connection, the device will send a FIN packet to the other device. Of course, with TCP, the other device will also have to acknowledge this packet. Let's show this process using Alice and Bob as we have previously. So Alice sends a FIN, Bob sends an ACK, FIN, and then ACK. And then, so everybody agrees that this is the end of it. In the illustration, we can see that Alice has sent Bob a FIN packet. Because Bob received this, he will let Alice know that he received it. and that he also wants to close the connection using Fin. Alice has heard Bob loud and clear and will let Bob know that she acknowledges this, and then that's it. So you can see TCP, even in closing the connection, expects things to be acknowledged. So even though we're literally like ending transmission or like ending the connection, we are still waiting and expecting an ACK or an acknowledge. Okay. The question here says, what is the header in a TCP packet that ensures the integrity of the data? It is a checksum. We have talked about this before. So provide the order of a normal three-way handshake with each step separated by a comma. All right. So it is a SYN. Sorry. Then it is a SYN ACK, and then it is an ACK. So the way to do that is SYN ACK, and then ACK. That means I want to synchronize, and the other device is going to say synchronize and acknowledge your synchronize, and then the last device will say ACK, which is I acknowledge. Okay. So we got task 2 right now. Let's get to task 3. Help Alice and Bob communicate by reassembling the TCP handshake in the correct order in the static lab attached to this site. Enter the value of the flag given. Okay. So the very first thing that we need to do is, let me reset this so we can see the entire thing here. And then the very first thing is SYN, and then we need a SYN ACK. And then we are going to say, yes, I can hear you. And then we're going to send an ACK. And we are going to say, cheesecake is on sale. I hear you. And then I can say, I'm all done. And then FINAC, yeah, me too. And then we are going to say goodbye. TCP chatter. So now you can see like how the packets and the SYN and SYNAC, the entire handshake is taken care or is being done essentially. Zoom in a bit. Now we're going to task 4, which is UDP IP instead of TCP IP. So all of that we've been talking about TCP and how it's establishes a connection and expects a SYN and SYNAC and stuff like that. UDP is completely different from this. The user datagram protocol, UDP, is another protocol that is used to communicate data between devices. Unlike its brother, TCP, UDP is a stateless protocol that doesn't require a constant connection between the two devices for data to be sent. For example, the three-way handshake does not occur, nor is there any synchronization between the two devices. So in UDP, you just pour the data in, just yeet it, and if it makes it, it makes it. If it doesn't, then whatever. Recall some of the comparisons made about these two protocols in Room 3, OSI model, namely UDP. Namely, UDP is used in situations where applications can tolerate data being lost, such as a video streaming or voice chat, or in scenarios where an unstable connection is not the end all. A table comparing the advantages and disadvantages, we will not talk about this again. We talked about it in the OSI model video. As mentioned, no process takes place in setting up a connection. UDP packets are much simpler than TCP and have fewer headers. However, both protocols share some standard headers, which are what is annotated in the table below. Time to live, TTL, source address, destination address, source port, destination port, and data. So we know all of them already from TCP. Next, we'll come on to discuss how the process of a connection via UDP differs from that of something such as TCP. We should recall that UDP is stateless. No acknowledgement is said during a connection. The diagram below shows a normal UDP connection between Alice and Bob in real life. Yeah, so you can see here, Bob just says, I want to connect to a voice chat channel or something. Alice says, okay, and then she starts sending boom, 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 boom. What does the term UDP stand for? User Datagram Protocol. What type of connection is UDP? It is stateless. What protocol would you use to transfer a file, TCP for sure, to have a video call? That would be UDP. Okay. So transfer a file, that you do not want to have half a file. You need to have the full file and make sure you got the file in the correct order so you can reconstruct it correctly. TCP is perfect for that. And then video call, you do not care if the video call just starts lagging a bit or you miss like some words. So that's why you want to have UDP. Let's talk about the practical here. And we have a bunch of things. So ports essentially are the gateway. So I'm not going to go through all of the ports right here because they are very easy to explain. So ports are essentially like every device, like your one device, your one computer, it can have multiple connections going at the same time. And the way to do that, and the way to know which application requested which data. So for example, you have Google Chrome requesting Google, but then you have Firefox requesting something else, for example. And this application is going to call a specific port on the server. So for example, just as a quick example, you could have the same server, like your own server, could be hosting a web server, and it could also be hosting MySQL, like a database, right? Then when your server receives a connection, it doesn't know which stuff or like which application, which service should handle this request, right? The only way it knows that is by the port. So HTTP is running on port 80. The MySQL is running on port, I don't even remember the default port for MySQL. Default to MySQL port, it is 3306, yes. So because the connection is coming on port 80 or port like 3306, it then knows that whichever application is listening for this port is the one that's going to receive this data and going to handle this request. All right, so open the site attached to this task, connect to the IP address 8888 on port 1234, and you will receive a flag. 8888 and then 1234, connect, and then you are going to receive a flag. So it is essentially super simple. You do have some default ports, but you don't need to memorize any of these. Like, you can easily just Google whatever port you're checking for. Okay. Extending your network room. Okay, so this is it for our room, which is related to network fundamentals, the packets and frames. The next thing is going to be extending your network, and it looks like we are talking about firewalls because this is what the icon here looks like a firewall. So I'll see you in the next video where we're going to start talking about firewalls. Now, as I've been doing the exact same thing every video that I end, I ask you to like, to subscribe, and to give me comments / constructive criticism. This channel is super new. I learned from the community myself. I studied for free. I learned everything that I know from YouTube and from free sources on the internet. So all I'm trying to do is to give back to this community. So I want to make sure that I'm actually providing value and you are getting usefulness out of these videos. So you can let me know this by giving me a like, giving me a comment, subscribe to see more videos if you enjoy this kind of content. And if there is something that you don't like or something that you think I can do better, let me know in the comments below as well. So that way I can do a better job of providing better videos and more value to you. My idea here, I'm not making any money from YouTube, obviously. I do have like 23 or 24 subscribers. So I'm not seeking money or fame here. All I'm trying to do is provide value because this is what I got my value and my career from, just for free on YouTube and other free sources. Like Stack Overflow, may it rest in peace now with the introduction of AI. But I learned from these sources, and all I'm trying to do is just give back to the community. That's it. Thank you for watching, and I will see you in the next video, which is going to be about extending your network. See ya.